Okay, so welcome everybody. So it's a Friday afternoon tutorial. You're almost through your first week back. Hopefully has been fun. So what we're going to talk about today is C++ templates, which is a form of what's called generic programming. Let's see if I can make this advance. Okay, so you've already used templates outside of programming. So you've made a resume, you probably wanted it to look nice. You might not have wanted to make all that formatting yourself, so you can download a resume template that has a nice layout, and you just enter your unique data, your name, your experience, your education, etc. So you can reuse this one template for many people. And today we're going to talk about the C++ equivalent of that, something called templates. We're going to talk about how do you write them, well, what are they, and what are they good for? How do you write a function template, which is a simpler kind? Then how do you write a class template, which is a little more elaborate? And then when should you do this? Okay, so templates in C++ are a way to do what's called generic programming, a way to write code that works for multiple types. C and C++ are called strongly typed languages. It means every variable has a type. You have to tell the compiler this is an integer, this is a double precision number, etc. That's done because it makes it easier for the compiler to find errors in your programs. So it helps you write larger programs that are correct. And it helps the compiler make your program faster. So there's some good reasons why C++ makes you do that. But it does mean that all the functions you've written so far work with certain data types. Like maybe they work with strings, maybe they work with floating point numbers, but what they can do is tied to the type they support. So we're going to talk about how we can kind of break that dependence. We can write this thing called a template in C++ for functions and for classes. You can use it for a few other things too that are not as important. We won't talk about those. Here's a reference, but this is the old 244 textbook, so I'll take this out of the slides because now I realize that 244 is not using this textbook anymore, so it's a reference to a chapter in a book that probably none of you own. Lots of online references for templates though too, so if you want more information, you can find it. Okay, so let's start with function templates. So I'm showing you a pretty common function here, a little utility to swap two values. Okay, so the top one takes two integers, a and b, and swaps them. Let's do a quick test of how well you remember 244. Okay, I've got this funny ampersand on both input arguments. Why do I have that? What's the purpose of that? Do I need it? Do I just like putting little ampersands all over the place? My house has ampersands drawn on the walls. Why is that there? Somebody's got to know. Yes, you in the back. Pass by reference. Is it important that I pass this by reference? Yeah, in this case it's important. If I didn't do this, I'd be swapping two copies which get destroyed afterwards. There's no point. So I need to pass the original variable, so when I do the swap, the calling routine sees that the swap has happened. So yeah, it's fundamental to what I did. That's just to make sure everybody remembers their C++ syntax. Okay, so that was it. I've got an integer version of this function, and down here I've got a double precision version. If you look at it carefully, you see that the only lines that have changed are basically all the ints on the inputs and on this temporary variable have turned to doubles. First, is this okay? Will this compile? I have two functions with the same name, different input types. Is this going to work? What do you think? Who thinks it's going to work? Quite a few people. Who thinks it's not going to work? A couple people think maybe not. Yeah, it is going to work. Anyone want to explain to me like what it's called? What makes this work? You probably learned this in 244 as well. You remember? Yeah. Yeah, so this is called function overloading. So C++ lets us have the same function name and just use different inputs to it. And the compiler is smart enough to figure out, well, these are different. I know when to use one versus the other. They actually generate different machine code, but the compiler allows you to use the same name and it'll figure out which one to call. So that's convenient because I wouldn't want to have like 20 versions of swap that all have slightly different names. So I can do this right now, and it's fine. But there are some downsides. I mean, the downside is that basically I had to write the same function twice, and I felt a little sad. You know, I wrote sort of the same code, and then I just changed the types. I didn't feel good about myself. I felt this was beneath my skill level. I should be doing more than changing one type to another for the rest of my career. And maybe 2 of them is not too bad, but maybe I need to swap strings, I need to swap floats, I need to swap complex numbers, etc. I wind up writing 5 or 10 or 20 versions of this. So it's kind of a waste of my time. If the functions are a little more complicated, you also could have bugs in them. Sometimes you're copying it and you're changing the types, you make a mistake. So one of them doesn't work properly. Or maybe you make 20 copies of it and then you find there's a bug in all of them. You got to fix it in 20 places. So you could do this, but there's some downsides. Get more code, it's a bit repetitive. If you get a bug, you have to fix it in multiple places. Okay, so this is what you know how to do right now. Write a function for every type, and I just told you the downsides. It's repetitive. If I find bugs, I got to fix them in many places. So the new option we're going to show you, or I'm going to show you today, is to write a template where the type can change. So the positive of this is that I'm going to write code that's a little more generic. It's called a template, and it'll support all types that compile. Okay, so basically, as long as the code I write makes sense for a type, it'll compile. That avoids code bloat. It avoids copying and pasting, which can lead to me making mistakes. If I find a bug, I fix it in one spot. So a lot of good things. There's a very small negative. The compiler has more work to do. The template is kind of a recipe, and it has to apply that recipe for every type. So it has a little more work to do to generate the machine code. Nowadays, nobody really cares about that. Compilers are pretty fast. And if you have such a big program that it's not fast enough, you buy more machines, right? And you compile it on multiple machines at once. So the only negative is pretty small. Nobody really worries about it. Okay, so how do I write a function template in C++? So I write mostly the same code I always would have. So here's my swap function. And if you look at the swap function, it looks an awful lot like it did before, the integer version or the double version, except I don't say that I'm passing in an integer A and an integer B, and I don't have a temporary variable of type integer. All of those things are now of type. Now what is type? Well, I have this, what's called a template prefix. So I have to write this little funny bit of code before I write a templated function. It tells the compiler what comes after is a recipe for making functions. So everything in purple here is a keyword. So template is a special word, type name is a special word. I use these special angle brackets. Type is called a type variable. So it's not a normal variable. Basically, it's a placeholder. And it's not a special name. I could have called that dog, but dog probably would have been confusing, so I called it type. It's just, that could be int, that could be string, that could be double. It represents some type, okay, so that I can refer to it. So I said, for my generic type, I'm going to call it type, and then wherever I want to use that generic type, I just use that word, just like I would have used int or double. Does that make sense? Okay, so now I've written the function template, and this actually just says what I told you already. So yeah, this type, when the compiler needs to make a function for a specific type, like int, it'll just replace this type with int and compile that code. Okay, so this swap function, I told you it'll work for anything that can compile, like makes sense. So if you look through all this code, you'll see that the only operator I use is the assignment operator. I use it there, I use it there, I use it there. So the operator equal or the assignment operator. Nothing else. So that means as long as the assignment operator is defined for the type that I try to use this with, the recipe works. Okay, the compiler can use it. Almost every type has the assignment operator defined, so it means my swap function is going to work with pretty much anything. Is everybody with me so far? Good? Okay. Okay, so how do we use it? So using it's really easy. In fact, you've been using function templates that are part of the standard library already in ece294. You just didn't know it. So here's a little main function. So I declare a couple integers, I and j. I print them out. They're 5 and 9. I call swap, and it's going to swap them. If I print them out after that, they're reversed. So that makes sense. Here I declare a couple of double precision numbers, x and y. Print them out. I call the swap function and print them out, and they're swapped. Okay, so normally when I call a function template, like I just do nothing differently. Like I just call swap. So that's what I did here. So let me clear all this text or all this highlighting. So here I called swap. I didn't tell the compiler which version. I didn't say int, I didn't say double, I just said swap. Compiler figures out, well, I and j are both integers, so I should make the integer version of swap and call it. So it works fine. Down here, I told it, I want to call the double precision version. And I told it that with this, again, angle brackets. The angle brackets is how you specify types to templates. I didn't have to do this, okay? If I cross out this double, which is what you would usually do, usually wouldn't bother putting that in, it'll just call swap, and it figures out X and Y are doubles. The compiler will build a version of swap for double precision numbers at compile time, and at runtime, that's what you'll call. So I don't need this double. I am allowed to put it in, okay? So I can put it in. If I put it in, I have to get it right. I said I want the double version of this. If I now tried to pass integers, it'll be wrong, right? The compiler will say this doesn't make sense. So that's why people usually don't bother writing this. It's more text, and you either get it right, in which case the compiler accepts it, or you get it wrong, in which case you get an error. So there's really not a lot of upside, but I'm just showing you it so you know you may see code that does that occasionally. But the more common way to do it is this. Just call the function, let the compiler figure everything out. Okay, so to quickly test comprehension on this, I'm going to get you to form groups of 2. If you're an odd number, you can form a group of 3. You can't form a group of 1, you have to join somebody else. Look through this little bit of code. So basically, you've got that swap function that I just showed on the previous slide. And this little snippet of code declares a few variables of different types and then tries to call swap a few different ways. So I want you to go through these and figure out, I'm going to give you a minute, with your partner, which one of these will compile based on the rules I just told you. And then to make it more interesting, to motivate you on a Friday afternoon, whichever team feels confident, put up your hand. I'll pick it. Multiple teams put up their hands. I'll pick one at random. If you get it right, you each get a chocolate bar. Okay? So this is a pretty good chocolate to effort ratio. So I would go for it. Okay, so you got a minute. You're not in a team. You might want to join them. How about that? I'm gonna bolt together a team of 3, or actually you can join her if that's okay. Join up someone. So, do you two want to join each other? You guys look lonely. Join each other. So, coding is social. Have a seat. So. All right, so you gotta talk it out. You gotta think through the rules that I told you, which ones are gonna compile and which ones not. Ready? What do you think? Are you guys ready? So I see at that side, you had your hand up. Okay, so I'm going to go to you. Who's your partner? What? I can't see your partner. Partner's hiding. Okay. All right. You guys ready? You got to say it loudly. You get first crack at this. Okay. Swap of m comma n. The first line. Is it going to compile or not? Okay. So it's going to compile. Why do you think it's going to compile? Just seems fine. Okay, sounds fine. Okay, what about this one? Swap of I comma n. Wait a sec, you guys had your hands up. I know it's a lot of pressure, but I could talk you through it. What do you think? Swap of I, comma, n. Even if you don't know, you got a 50-50 shot. You thought it wouldn't compile? Yeah. What is your, okay, but is that your guess? You're doing this very tentatively. It almost seems like, well, I thought it wouldn't compile. My partner thought that it would. So I guess we're right either way. Can't do that, okay? As a team, you guys have to make a decision. Compile or does not compile? Okay, so you say, here's your answer is it will compile. Okay? Is that right? Okay? You don't think so? Okay, confer with your partner. And then I need one answer. So you say, it says, you put your hands in front of your face. I got to say, your body language is, I am not confident in this answer. You're not selling it. You got to sell me. Okay, I is integer, n is a character. Okay, okay, so you say, interesting. Okay, now, can I encode just write, can I set a character equal to an integer? Like, does C++ let me do that in code? It actually does, right? But it does lose precision. So it'll do an automatic conversion. You're saying no automatic conversion here, right? An integer is not a character. They're not the same. They're different sizes. Won't work. Okay? It's good you stuck to your guns. You are right. Okay? So I'm not trying to confuse you. I was just making sure that you were solid in your answer. You're exactly right. The types have to exactly match. If you look at this, it says type, some type, and the same type. Okay? They must be the same. They must not, it's not close, like, well, int's kind of like a char and so on. No, identical types. All right? Otherwise, the creators of C++, even though there are automatic conversions between things like integers and characters, they went, we have automatic conversions and we have these generic types that match anything, and you put all that together, no one is going to be able to figure out what's going on, right? It's going to be chaos. So templates will do absolutely no conversions. This must be exactly one type the way I've written it. So you're right. Okay, what about this one? Yeah, so I kind of shot myself in the foot here. It would have worked fine if I just gave I and j and didn't put this double, but because I said I'm so clever, I'm telling you it's double, and then I gave you integers, it won't work. If I just left this double out, it would have been fine. So in real life, don't put the double, okay? All right, what about this one? Swap of int ij. Sorry, say will or will not? Okay, it will work. I do have a feeling that at the end of this lecture, I could sell you a car. And I have a very old minivan I'm trying to get rid of. My wife hates it. So we'll talk after. So one lecture last term, the radiator gave out, and the next lecture, the electrical system gave out, and I could not use my turn signals. So every single traffic light I came to, I just flashed by 4 ways. Nobody knew which way I was going, but they knew I was doing something. So anyway, maybe I'll sell you that car. Swap character x comma j, or x comma y, sorry. Won't work, right? Because the character does not match. These are doubles. Would have worked if I just left this character out, but I didn't, right? So yeah, there's not really much upside to telling the compiler things it can figure out. And let's see. Let me click on this. So yeah, so you got it exactly right. Okay, so you two come up here, pick a chocolate bar each, all right? I'm not going to deliver them for the interest of time, but that was well done. You were a little tentative at first, but you got into it. You eased into it. Okay, so now I'm going to have you guys implement a templated function just to get a little bit of experience with this. So all templated functions start with this template prefix. So template, type name, and then a type variable. So I'm using the word type, doesn't have to be that. Name of the function is going to be minimum. It's going to be the minimum of 2 things, okay? Like an A and a B. So what should we write for the arguments here? Let's just call them A and B. But there are 2 arguments. What should their type be? What do you think? Yeah. Type A, type B. Basically, I said that the generic type is name type, so that's what I should have there. What should it return? You're on a roll. Go for it. What do you think? Should return type. So that's exactly right. And I don't want to bring all these chocolate bars home for the weekend, so grab a chocolate bar, okay? So if you would like one. If anyone does not want a chocolate bar, you could always donate it to the class. It's fine. Okay, so procedure. You're going to go to this IDE that hopefully you've already signed up for. So go to this URL, https://codeboard.io projects 206059. Okay, so we've set up a little project for you. There's code in exercise 1.h where you basically have already given you the skeleton of this minimum function. Fill it in to show that you can write a template. You hit compile to compile it. You hit run to run it. We've got a couple of test cases. You can see if it works. So I'm only going to give you 4 minutes to do this. It's not graded. You don't have to submit it. This is just for you to try writing a small amount of code really fast to see if you got this concept. Okay, so go ahead. I'll be back in 4 minutes. Good, you guys all got there fast. It's good. How's it going? Let's see. Looks like you did it really fast. Hit compile. Make sure it compiles. Okay, now hit run. And the run, we have a main program that basically, so you can see you can look at it if you want, but basically the main is just calling it with a couple of integers, and you said 4, and then it called it with a couple of characters. You said C, so looks good.
Is there a prize about
This one I didn't have a prize for, but you could argue for it. So don't worry, there'll be lots of options. I'll keep asking questions. Just there's lots of chocolate bars. I got to get rid of them. So it's a buyer's market. So. I'm going to use you guys as the candy store over here, if that's okay. I'm going to use you guys as the candy store. How's it going? Did you make it work? Yeah, looks good. So if you look in the main, you can see it called it with integers, then it called it with characters, and both of it works. Going okay? Cool. So you compile it and run it to check that it works. Nothing, I mean, it probably works, but really most things don't work until you do it. Okay, press run, and the main function basically makes a couple of calls to it. So you can see there's a couple integers that are given to it. It returns the minimum, a couple of characters. If you look in main.cpp, you'll see the test, which is not very complicated. So, but you could write another one with strings or whatever you want. It'll work for all of them. Okay, has everybody had enough time? You guys are done writing it? Okay. So let's keep on going. Let me make sure I'm still recording. Okay, I still am. Okay, so your code probably looked something like this. So we got the template prefix. We've defined our type variable type. We use it in our header. We don't even need any temporary variables here. I used operator less than. So if A is less than B, return A, otherwise return B. What could I use this minimum with? Like what do I need to exist for a type or a class? Class is just another kind of type, in order for this template to work. Yeah. Yeah, so that's the only operator I used. So as long as that exists, this will compile. If I use it with something that doesn't have operator less than, it won't compile. If I had written this the other way, like I could have written this with a greater than operator, okay, then I only need operator greater than to work. So templates are kind of easy to understand. You can think of it as like the compiler is like pasting in types. And as long as what happens compiles, it's happy with it. It's fine. Okay, so we already talked about this, and exactly when type is used. Oh, I guess we didn't say that, but I think you already have that rule. If I was to pass in an int and a double, this is not going to work, right? Because they're different types. This only works for one type. That's the way I wrote it. And then all of the code that's, everything that I have in that function has to exist for a type, which in this case was only operator less than, so it's going to exist for almost every type I use. Okay, so that was function templates. We can also write class templates. So part of class templates are just like function templates. All your member functions are just functions, so pretty much they're the same. But we can also template the member data. Okay, so what would be examples of this? So we could make a templated linked list, for example. Okay, so that's one of the, where we usually use templates in classes, or what the most powerful way to use them is for basic data types. So in ece294, I am pretty sure you will have written a linked list. Did you guys write a linked list as a lab exercise? Did you write one linked list, or did you write a couple different types? How many types of linked list did you write? 2, 3, 1? I'm guessing it's more than one type. Yeah, so I taught 244 years ago, and we'd have like linked lists of integer registers and linked lists of capacitors and so on. With templates, like what you notice when you write your second linked list is that almost all the code's the same. The only thing that's different is the data that you're carrying along at every node. So you can template that. You can write a linked list once using templates and then basically ask for a linked list of anything, of resistors, of capacitors, of integers, of doubles, of strings, whatever you want. So it's a great use of templates. And you can do that, that's done for all sorts of basic data structures. Templated arrays, templated binary search trees. You also learned how to write binary search trees. They're kind of complicated. You'd rather not write one for every single thing you want to put in a binary search tree. Much better to write a template. But in order to do this, we have to template not just the functions, but also the data, like the member data. Okay, so I think this is a lab that I made in 244, which appears to have not survived the test of time. It did for many years, but I think you did not write a binary search tree in ece244. Is that right? All right, so let's pretend you had. Okay. Let's just say that you're writing a binary search tree. It's pretty common to have, well, all binary search trees have a key and a value, right? And the key could be any type, and the value could be any type. So let's say, for example, I want to look up student numbers by the student name. The key is a string, and the value is an integer. But that's not the only kind of binary search tree I can make. I mean, I could also look up things by integer and return a string, right? So I could have my key as an integer, my value is a string. My key could be a string, my value could be an entire linked list. Could be all sorts of stuff. So we're going to create a templated kind of basic data type, but we're not going to do a binary search tree. It's a bit too complicated to do in a tutorial. We're going to do a really simple templated class. But this is still actually a useful class. It's a class that can store 2 arbitrary pieces of data. So, and we can't give those pieces of data very good names. So we're going to call them the first and the second. And the first is of any type we want. We'll call it first T. And the second is of any type we want. We'll call that second T. So this data type is often called a pair because it just groups 2 things together. You just call it, you can ask for dot first, you can ask for dot second. Why is something so simple useful? It's useful because you need pairs, key value pairs, to do things like insert or retrieve data from a binary search tree. So this is a useful building block class. So if I have this pair, I could do things like take a binary tree and say insert the following data, and the data I want to insert is a pair. It's a key and a value. Now I could make all sorts of different classes that store different keys and values together, but if I make this generic pair, I've got a recipe for storing 2 arbitrary types of data together in a class. So I can kind of write it once, and then I can use it over and over again. Does that make sense? So it's kind of like the simplest templated class that is useful that I can think of. So that's the one we're going to write. Okay, so this just repeats kind of what I said. This pair object is an association of two different kinds of variables. So we've got a first data member, and it could be whatever we want. So here I made it a string, and the particular object stores apple in it. And then it's a second data member, and here I've made that of type int, and this particular object has a 4 in it. But I could make a different kind of pair using this template recipe. So the first could be of type double, and the second could be of type string. Okay, so template is a recipe. I've made two different kinds of pairs here, and then I made an object of each type. Is everybody kind of with me so far? None of this, seems super fancy. You're like, well, I could make normal classes to do this too, and you could have. Okay, let's look at what the code looks like. So this is basically just the class definition. Looks like a normal class definition. It says there are public functions. This is a constructor. This is a setter for the first member. This is a setter for the second member, and so on. But before I write that class, I put this template prefix, just like I did for functions. So again, it has the keyword template, it has this funny angle bracket, it has type name. But this time I'm not saying there's one type name, like type variable. There are two of them, one called first t and one called second t. And it's common to capitalize the first letter of a type. You don't have to, but it's a good coding convention to show that that is a type. Okay, so basically this is like my type in the previous example, but I've got two of them now, a first type and a second type. My constructor, so this is a constructor. It basically just says you're going to give me some first val and some second val. I'll use that in my constructor. And what are their types? They're not int or double. They're just some generic first type and some generic second type. My setters, they look like normal setters, right? So I'm going to pass in a first value for the set first. I'm going to pass in a second val for the set second. But basically, I don't know their types. I only know that the type variable, the name that I gave this type is first t in one case and second t in the other. And again, I have getters, right? So I've got a get first here, and it returns something of first type. I've got a get second, it returns something of second type. Okay, and then finally, I've got my private data. And this is a very generic class. So all I can say is I'm going to call my first data member first, my second data member second. What are their types? Well, they're these two type variables. So it could be anything, but I've given them these type names. Does that make sense? So if I just changed first t to int and second t to string, this would look like any normal class that you've written, like a very simple class. But I don't want that. I want to make it more generic so I can make pairs of anything. That's why we're using this templating style. Okay. One note about writing classes that are templated. In C++, you normally write just the interface of a function in the header file, unless the function is really short. Okay, if it's really short, you might write the whole body. But if it's longer, you normally don't write the whole body of the function in the header file. You write that in a C++ file. For templated functions and classes, you put everything in the header file. And the reason you put everything in the header file is because the compiler, as it's going through your code, it's figuring out what types of pair you're using. You're using this recipe with an int and a string. I'll make you the code for that. You're using this recipe with a string and a double precision. I'll make you the recipe for that. In order for that to work, it basically needs to be able to see the recipe as it's going through your C++ files. So that means that the whole recipe, all of the code for this templated class has to be in the .h file. Does that make sense? So normally for longer functions, that would be considered poor style. Like it's not wrong, it's just considered poor style. For templates, it's not. Just because of the way compilers work, you have to do it. Does that make sense? Okay, so I showed you essentially the interfaces to some of these functions. I didn't show you their bodies. Their bodies are not very exciting either. So here was the constructor that I showed you. And its body is just initialize this first data member to whatever you passed in as first value, initialize the second data member to whatever you passed in as second value. The set first function is also simple. Just set my private member variable first to whatever you passed in to this function. So there's nothing magic about this. They look just like regular code. The only thing that's different, again, is the types are generic, right? We're using this first T and second T instead of things like int and string. Okay, how do I use pair? So to use a class, I first have to make an object, right? I make a variable of that type, and then I can call its member functions. So this is a variable, pair1. What's its type? Its type is it's a pair. Now, pair is a recipe. A templated class is actually a recipe for making classes. So I have to say what kind of pair I want. I want a pair where the first data type is int and the second data type is float. So I have to tell all of that to the compiler, and that is all essentially part of what is the type of this variable I made called pair1. And I'm going to initialize it using its constructor. I said I wanted an integer and a double, so I pass in an integer and a double to the constructor. And then I can do things like print out what's inside of it. Okay. So this line basically makes an object in memory, just like any other variable declaration. And this particular object stores an integer, which is initialized to 1, and a floating point number, which is initialized to 2.5. And it has enough memory storage to store those things and so on. Okay, so here I make another object. Okay, this one's called exam. And it's also using this recipe pair, but it is different because it's making the first data type a string and the second data type a double. Okay, and it also calls the constructor and it passes in the appropriate types to initialize those things. So after I hit that line, I've got this other object called exam in memory. And you notice it actually is a bit bigger even. The amount of storage it takes is different. So it is made with the recipe pair, but it is actually a different type because it's got a string as its first data member and it's got a double as its second data member. And I can call the member functions on it too. Yeah? So that's a great question. That question is so good that in the break, you're going to get a chocolate bar, okay? Because that was not an answer, if you want one, but that was not an answer, but it's a great question. So the question is, can I just leave this out, right? Because for functions, I said, yeah, you can put it in, but what's the point, right? The compiler will figure it out if you don't put it in. For creating this variable, pair1, I have to put it in. It's not optional. Okay, so why do you think that is actually? So I'm going to pick on you to basically, so it's a great question. Do I have to do it? I do have to do it. But for functions, I didn't, right? Functions, it was totally optional, therefore almost nobody puts it in. But here I have to. Why do you think the compiler makes me put it in here? Well, so it's kind of fundamental to the language. Like there's a very good reason of why it forces you to do this. So in a function call, I have existing variables that I'm passing into the function, right? In this, where I'm declaring a new variable, the compiler does not know what this variable is, right? It doesn't exist yet. You're actually saying, make me a variable of this type, a pair with an int and a float. So if I left out the int and the float, it's ambiguous. Like, what do you want? You've told me you want me to use recipe pair, but you haven't told me what kind, right? Now, some people go, well, wait a second, but you called the constructor, right? And you called the constructor with an integer and a double precision number. So couldn't the compiler look at that and say, well, you must want a pair with an int and a float? You could try, but it's unsafe. You're allowed to have many constructors for a class, and that's actually common. So I might have like a default constructor with no arguments, a constructor that takes one argument, one that takes two, maybe even other stuff. So there's no safe way to try to figure out just from a constructor call, what are you trying to do? And in programming, you spend most of your time actually debugging and making sure things work. So you're not doing anybody any favors by saying the compiler's just going to guess. Maybe it guesses right, maybe it guesses wrong. Who knows what your program does, right? Like that's not helping anybody. So the creators of C++, basically that's madness. When you want to make an object, you must be explicit. Tell me exactly how to use this recipe because I cannot guess it. Does that make sense? Okay, so great question though. Okay, so I'm going to do a very short demo and then we'll take a break for a few minutes. and then don't go home because we'll get back at it after that. So, okay, so let's see if I can find my VNC session. Okay, so I'm going to show you a really simple templated bit of code. Is that big enough? Can people see the screen? And can you read that? Because I can make it even bigger. So seems like I can't help myself, actually. I'm going to make this one step bigger. Yeah, that seems even better. Okay, so this is a very simple piece of code. I've written a templated max function. Let me get rid of that black bar. Okay, so I've written a templated max function. It looks just like the min function that you wrote, but backwards. And then I've got a main function that calls it with a few different things, right? So create a couple double precision numbers, call max, create a couple of integers, call max again with double precision, and just print out the output. Okay, so there's not a lot of code here. So is this going to compile? And I'm not above bribery, okay? So fine, if you answer this correctly, I'll give you a chocolate bar, or you get one in the break. So what do you think? Is this going to compile or not? And even if you have no idea, you go, wait, I got a 50-50 shot, right? It's not bad. I just go for it. And in fact, if I got a partner beside me, I could cut a deal. I'll guess yes, you guess no, we split the chocolate bar, right? Like, it's so easy to game this. Yeah, go ahead. It's going to compile, okay? Okay, so you think it's not going to compile. Sorry. I'm going to go to your partner. Hopefully you cut that deal with them. that you're getting half the chocolate bar. So what do you think? It's not going to compile. Actually, you guys have to split the chocolate bar, because I mean, by him going one way, you had it afterwards, right? So, because if you said it's going to compile as well, then for sure, no chocolate bar for either of you. So it's not going to compile. Why is it not going to compile? Oh, wait a sec. You were just playing the game. You guys really did make a deal. Okay, it's not going to compile. Which line is going to be the problem? Anybody know which line is going to be the problem here? The reason I'm doing this one actually is it looks like it should compile. Okay, so templates, they are very handy, but you can get these compiler errors that seem a bit baffling. So that's why I'm showing you this, because it looks like it should compile. So I want to show you why this doesn't compile, and then just how to read the error messages. Because when you use templates, sometimes you go, well, why doesn't this compile? So do you have a thought? Yeah. Do you think you know? This one, double D, that is the line. It will not compile. Why will that line not compile? Right? Oh, actually, sorry. Okay, wait a second. I actually forgot to change this after the previous tutorial. This one will compile. I totally have to give you both chocolate bars. In fact, okay, so that was a trick question, because that is actually supposed to be what it is. But I fixed this for the prior. Okay, you don't tell them the other tutorials. I'm going to give chocolate bars to you two and you. That was an impossible question, okay? Because I believed I was asking a different question without the dot. Okay, now you're right. That's the one that will compile, and I think I've given it away. It's because that's a double, and this looks like a double because you think, well, 2 is a double precision number, but to a compiler it's not. It's an integer. It can convert it to a double, but it will not convert it. You have to put the dot in to make it compile. But you can get errors like that kind of like, you know, this looks right. Why doesn't this compile? Yeah. Because by default, without an F, it's a double. Okay, that's just the rules of C++. So yeah, you can get some things where you kind of mathematically, you know this makes sense, but the compiler is very strict. No conversions at all. We're not converting an integer constant to a double precision. So let me compile this to show. Okay, so it's kind of a hard fail for me on that problem. Sorry about that. I'll look at the cases carefully on the next set. Okay, so if I build this, do you guys use make it all in 244, or do you always use an IDE? Okay, so you know that you can type make in a command line. It's the same as pressing build in an IDE. Okay, so I just typed make. It invokes G++, the compiler we're using. You're going to notice this in the projects we give you. We turn on these W options are basically turning on extra warnings. Warnings are your friend. It's the compiler looking for funny code. But basically, we get an error. And the way to, and actually for that one thing, that one dot, I got about like 8 lines of error output. And for more complicated template errors, you can actually get 20, 30 lines of output. So it can be a bit intimidating at first. You read it from the top down. So this says line 17, character 24, and it actually points at it. So this bracket basically says I couldn't find a matching function call to max of a double and an int. This is the most important message, right? This is what really went wrong. Okay, could not find any function that matches what you're asking for. And then it tries to give you some helpful information. It says I almost match this. You have a templated max function that returns a type, takes 2 arguments of the same type, but it basically says I couldn't figure out what this type is. This template argument deduction failed. That means I couldn't figure out the type because this parameter t, there's only one of them. There's one type here, and it has to be both double and int, so I can't do that. So that's how you read these messages. The first one is the most important. It says I could not figure out how to build this, and then the rest are hints. I almost could match this, but not quite because it's a double and an int. If you read that carefully from the top down, you hopefully would go, oh wait, that is an int, and therefore I should do this, right? The fix, once you figure it out, is very simple. So I just put a dot here. That will now be double precision. Whoops. Now if I build it, it works fine. Okay? So yeah, I owe 3 chocolate bars for asking an impossible question. Sorry about that. Or not the question that I thought I was asking. Okay, so one last slide and then we'll break for a few minutes. Okay, so tips for writing templates. So I just showed you template errors can be complicated, and they can be a bit overwhelming when you start out, because that was a pretty simple templated class. So they can actually get more messy than that. However, you don't have to write many templates. In fact, in this course, you probably won't write any templates. I've been teaching you the syntax because it's useful to be able to read it, but you probably won't write templates in this course. The reason is there are a lot of templated functions and classes that already exist in something called the standard template library, or STL. So what I'm going to talk about in the next half of this tutorial is we're going to start going into what's in that library. If you decide to write a template, most coding is really about debugging, right? It's not about writing the code, it's about making it work. So you always want to minimize your time, minimize the amount of code you're testing. If you can localize it to a very small amount of testing or amount of code that you're testing, you're much more productive. So if you want to write a template, what you do is you write code for one type first. So I'd write the max for integers, for example. I would test it, make sure it works. Then I'd go in, I'd change all the integers to type, and then I would test it again. First I'd test it with integers, then I'd test it with doubles, then I'd test it with some other stuff. So I'm breaking my tests into smaller pieces. Don't try to write the templated code right away. Write something specific first and then convert it. Okay, so with that, we'll take a break till 4:10, and then we'll get on to the second half of the tutorial, which is going into that standard template library. Okay, so we're gonna get going again. I have a design challenge for you guys first, okay? So I'm gonna challenge any 3 students. Okay, so let me give the motivation. Right? I told you that practice is important, right? It's good to practice at skills you want to get good at, software you should get good at, so practice. Okay, so I have 3 daughters. They're getting older now, but I've spent many years playing Mega Blocks with them. Mega Blocks are like giant Legos, okay? So these are Mega Blocks. And we built the Golden Gate Bridge out of Mega Blocks, not full size. But okay, so I think I've had way more practice with Mega Blocks than anybody here. So I'm going to challenge any 3 students to build a house out of Mega Blocks and see who can do it faster to show you the value of practice. To make it more interesting, I'll give you a head start. Team of 3. And if you win, you get a chocolate bar each. Okay? So who would like to form a team of 3 here? Okay, so let's see. I'm looking around. See if we can see anybody who haven't. Okay, so you 2, you're in. Are you in with them? Okay, you 3, you're up. Okay, so go over there. This is your bag of Mega Blocks. Familiarize yourself with them. Let me see if I'm recording the lecture again. Okay, so familiar, nope, those ones are mine. So I'm gonna give you the bigger bag. Don't want anybody to accuse me of like being unfair. So you take them out, start looking at them, start planning. Okay, so we need rules. We need a timekeeper. Do you want to be timekeeper? Okay, so you get a cell phone. I think every student has a cell phone. You're gonna time this, make it official. Okay, so the rules. You're also gonna be the judge. Okay, hold on guys, you gotta hear the rules. If you don't hear the rules, then I can totally say I won no matter what. So, a house has to have 4 walls and a roof. It has to stand on its own, can't fall down, can't be holding it up. Can't have any major holes, you can have a little hole. And from the bottom, it has to be open so that at least one team member can put his or her fist inside of it, okay?
From the bottom.
From the bottom, right? Because that shows that you didn't just build a solid block. I'm eliminating that possibility, okay? It's got to have enough room to put one fist in it, okay? Otherwise, it's up to you. Got it? Are the rules clear? You can dump them out if you want, it's fine. That's fine, don't worry, they won't break. Okay, so to get in the right spirit though, let's get some friendly competition going. See if I can turn this up a little. Okay, wait, the timekeeper hasn't said go yet. Come on guys, you can plan, but okay, take that apart. Okay, ready? Yeah, that's stopwatch is fine. Okay, go ahead. Start. Okay. Walls have to join. They have to join. You guys, if you want to get a closer look, you can come see their plan. I don't know if a fist is going to fit in there. I don't know. All right, well, I'm going to go in here. So, let's see. Yeah, maybe that one. Maybe that. Maybe this one. Yeah, those go together. Oh, and this looks like a fit. Done. Done. Who won? Oh, they were close. They were close. So. Well done, right? So. Okay, so what was the lesson of this? That's right. Okay, so one lesson might be that I cheat. I did cheat. Okay, so you guys did actually very well. You can have a chocolate bar each. You were close, given that basically you're building stuff out of low-level C++. Okay, that's good to know, but you're building things out of things you learned in 244. I'm using prefabricated components, so I'm basically using the standard template library. So I had 4. You're building out of blocks. I built out of 4 walls and a roof. It's a lot faster. So you want to learn how to use STL because you'll build things much faster. Okay. Anyway, but good effort. You're almost there. So, and so help yourselves to a chocolate bar. We're going to call it a tie. So if you guys want to, I think you guys want to finish the house. Go for it. So. So there was one other thing I was trying to demonstrate there. So the main thing was the value of templates, right? That you can, if you use the right components, you can do things a lot faster. Do you think there's anything else within the context of this course that I might have been trying to emphasize there? What do you think? What's that? Reusing code, but this one's not actually software. So the other thing I was trying to show you is it actually has nothing to do with software. Okay, so think of the goals of this course. What other goals are we trying to emphasize? You guys have already forgotten. I guess we failed at that. So one of the other goals of the course is try to make memorable presentations. How do you say things so people actually remember what you said? They understand it, they remember it, which is a lot harder than it sounds, and it's important in teaching, it's important in industry, it's important in research. If you can't explain it in a way that people remember, it doesn't have any value. So I could show you, and I am showing you, snippets of STL code, and I'm saying STL is good, but my assertion is that you will remember this longer than you remember the pieces of code that I show you. So did I use any made to stick principles here? It's visual, but visual is not like a made to stick principle. So yeah, so it's probably unexpected. You probably didn't expect me to cheat. Like first, unless you talked to the other sessions, probably most of you didn't expect to come here and see the instructor start playing with building blocks. That was probably a little weird. And then for me to actually cheat at it seemed a bit even more strange, right? So, but that's on purpose. Hopefully you remember that experience. There's another one that I'm using too. So what other made to stick principle kind of shows up here pretty clearly? If you remember those, maybe you haven't read the book yet, but remember there are like 6 principles that spell the word success. Any other principle that you can think of for this one? So another one of the principles they use is say, make it concrete, right? People tend to, they remember concrete things better than they remember abstractions, at least until they become experts. Once you're an expert, sometimes you can remember the abstraction. So this is concrete because you can see it, you can touch it, etc. So I was trying to like, yeah, get the point across in a different way. Okay, hopefully that made you want to use the standard template library. You're like, whoa, how can I win contests like that? So we're going to start, the standard template library is very big. So we're only going to cover part of it, and that's fine. You know, most programmers don't know all of it. They look things up when they need to know it. That's standard practice. So what I'm going to talk about today is why should you use it? One of the most important templated classes in the standard template library is called vector. So we're going to talk about how that works. Basically a better array. So we'll talk about when you should use it and how does it work. Okay, so why should I use the standard template library? And let me make these floating meeting controls go away. There it is. Okay, so I already told you this, writing templates is actually a little bit harder than writing regular code because it's more abstract, but using templates is much easier and more productive. So it's best to use the pre-existing routines in the standard template library rather than write your own whenever you can. So an example is like a sort function, right? Standard template library has a lot of really fast sort functions. They work for anything, right? Any object that has a comparison operator defined. Why write your own? What's in the STL? Lots of stuff. So there are functions like swap, sort that are useful, and min. There are classes like the pair class that we talked about is in the standard template library, and lots of other things that aren't listed here. The most important part of the STL, in my opinion, is the containers library. So the containers library are these kind of fundamental data structures written as templates so you can store anything you want in them. One of those data structures is, well, one that you know would be a linked list. So you wrote this in 244, doubly linked list. You don't have to ever write a linked list again in C++ if you don't want to. You just ask standard list. And in fact, you probably shouldn't write another linked list. Standard list is well written. You just ask for a linked list of the right type. There's another very important container class called vector, which is what I'm going to talk about. Vector is basically a better array, okay? And I recommend that you use vector instead of what we call C-style arrays in this course, and probably generally in your career. Okay, what makes the containers library really useful is all the data structures are templated. So vector, as I said, is like a better array, and you can store anything in it. So here I said I want a dynamic array or a vector of doubles. Here I said I want a linked list, and I want a linked list of strings. So it's the templating that makes this really powerful. Okay, so next week we're going to talk about some of the other container classes. Basically all the fundamental data types you'd want are already written in the STL. Today we're going to talk about one of them, vector. Okay, let's start with why we might want to use this. So as I said, vector is like a better array. And one of the things that it can do better is kind of highlighted by this example. So let's say we want to read a bunch of integers from a person sitting there typing at a keyboard until he or she hits Control D, which means end of file. Okay, so maybe the person types 5 integers in and then hits Control D. Or maybe the person types 10,000 integers and then hits Control D. We don't know. We don't know how many numbers this person is going to type. But we want to take all these numbers in, put them in an array. And the reason we want to put them in an array is very convenient, right? An array gives you very fast random access. You can get at the first entry, the 10th entry, the 10,000th entry, all in order one time. So arrays are really nice. So I want the data in an array. But I have this challenge of I don't know how much data there is until I'm done reading it. So how can I put this in an array? Or any solutions of how I could read this in? So basically, if I just say I'm going to make an array of size 6, like I say, give me array equals new int of 6, well, if the person types 7, I'm in trouble, right? I could say, give me a new int of 2 billion, but now I'm wasting enormous amounts of memory if the person only wants to enter like 3 things. There's no really good solution that's simple with an array. So any other ideas? Don't worry, I won't make you code it. Do you have any other ideas of what you might do? So my idea right now is, well, maybe I'll just allocate a really, really big array. And hopefully the user never types more than that number. Which is not a good solution, but that's my solution. Can anybody come up with anything better than that? Yeah. Yeah, so I could use a linked list, because a linked list can naturally grow. And let's say I don't know about the STL, so I'll write my own linked list. Now I want it to be in an array after I'm done. So can I do that? So I could. I mean, I could put it in a linked list, and then once I put it in the linked list, I could go through the linked list to count it. And now I know how many things to put in the array. I could actually say, give me an array of this size, so using new, and I could copy everything over. Okay, so knowing what you know from 244, you could write this. But what I just described sounds like an awful lot of code to do what sounds like a simple task. It's doable, but it sounds like a pain if you write all this by hand. So yeah, so that's one of my solutions, would be to put it all in a linked list. But because they're inefficient to go back and forth through, I'm going to like go through it and copy it to an array before I'm done. It works, but I wrote an awful lot of code to do this. Okay, so a better solution would be, what if somebody gave me an array that can grow dynamically? Like I didn't need to know how many things were in it when I started. If I needed more space, I had a member function that would make me more space. That would be really convenient. It would perfectly fit this problem. And I still want it to be fast, right? Like a list can grow when I need it to grow, but the problem is it doesn't give me efficient random access, so I don't like it. So I want to be able to grow an array dynamically, but I still want it to behave like an array, that I have order 1 random access. And that's exactly what a vector does. Okay, so let's look at how you use a vector a little bit. It looks a lot like an array. It is basically a better array. So you can use the subscript or square bracket operator to get at any entry. So here, for example, I'm getting at entry 40, index 42, which is the 43rd element. Just like arrays, vectors start at index 0 and they go up by 1. So I basically have taken whatever's at that entry and I've stored it in some value, some integer. So I could do that with an array too. That code looks just like an array, and it's just as fast. But I can also do things like this. So my vector is just the name of some object I've created. It's a vector, and I can call a member. I can call its member functions. This is a class. So vector has a member function called pushback, and let's say this is a vector of integers. This call is basically saying push back, or at the end of this vector, I want you to make a new element, and I want you to store the number 5,128 in it. So that's what this call did. This is something I can't do with a regular array. So I said, make one more entry in the vector and put this number in it. I can modify entries in the vector, and this is again just like an array. So here I'm saying take index 42 and put number 64 in it. And a vector is a little more convenient than an array because it knows its size. So when you have dynamically allocated arrays, you've probably noticed in your code that you usually have to have a counter of how big it is in another variable. A vector stores that internally. So I can say, call the member function .size, and it'll return how many elements are in the vector. So that's convenient. Guys, can I get you to quiet down back there? Getting a lot loud back there. Okay, so let's look at how I would use this to solve the problem I just talked about. So if I want to use class vector or templated class vector, I need to include the proper header file. The header file name is vector. You don't have to memorize that. I'm going to show you a couple reference sites at the end of the class. You look it up if you forgot. And I'm going to make a function called getIntegers that solves that problem that I talked about. Somebody's typing in integers until they hit Control D. I'm passing in a stream. You guys know what streams are? Did you study that in 244? Yeah. Okay, so cin would be one stream. It's an important one, but it doesn't have to be cin. But let's say in this case, we're going to pass cin in. And I'm going to return the vector. It's a vector of integers, because I know the person's typing integers. And that's what this function is going to return. So, and I'm going to need a temporary variable, and I'll call that variable integers, and it's going to be of type vector of integers. So this is like the start of my function. Now I need to write the actual code. Let's see. Are you familiar with this notation where I have std : : Yeah. So in 244, did you usually do this? This basically says I want something from the standard library namespace. The thing I want is vector. So standard library puts everything in something called a namespace to avoid polluting your program with lots of short names. You can either do this, basically give the full name, which starts with std : : or you can put it at the top of your program using namespace std. What did you usually do in 244? Yeah, so it's shorter. This is considered somewhat better style, although you'll see in some examples I get tired and I use using namespace std sometimes too. But this is considered a little bit better style, because the whole reason the standard library put things in a namespace was to avoid, essentially having names of things in the library that conflict with your names in your program, and using namespace std kind of defeats that purpose, because it pulls all the names in. So this is considered a little bit better style, but it is a few more characters. So you're going to see that in our examples. Okay, so this is all the boilerplate. I got a function. It's going to read from a stream until the stream ends, and it's going to return a vector of integers. So this line is making my temporary variable where I'm going to do my work. And this is a variable, this is a type. The type is recipe vector of integers, right? Vector is like a template, it's a recipe. So I want a vector of integers. I just called it integer. I didn't put anything in brackets, so I'm getting the default constructor. The default constructor of a vector does what you would imagine. It makes an empty vector. So the vector is size 0. It doesn't have anything in it yet. So that's what I start with. And this is what the code looks like. There's a bunch of ways to write this. So I'm declaring an integer variable value for whatever the person typed most recently. I have a while loop. Basically what this while loop does is every iteration through the while loop, it takes one value out of the stream. And the condition will be true as long as the stream is not in an error state, like as long as I haven't run out of inputs. So this short little while loop means keep reading from the stream as long as the stream is valid. I haven't hit end of file. So I read one integer at a time. When I get that integer, I've stored it in this integer variable value. I basically say, call the pushback member function in vector, right? And the way I call a member function is just this dot notation, as you know from 244. So that means take this new value I just got and put it at the end of the vector. And it creates space for it. Like it basically makes the vector one bigger and sticks that number in. And when I'm done, I just return my vector. Okay, so the code's very short now, right? The fact that this vector can grow has made my life a lot more easy. And I'm growing it with this pushback member function. Okay, so hopefully that made sense. Now I'm going to give you another short exercise. So you're going to go to code board, I'll show that in the next slide, and you're going to write a function to print a vector's elements. So we'll give you the header and so on. You're going to print it out with a for loop, and you don't need much. You basically need the size member function, and you need to use the square bracket operator, the indexing operator. That's enough to print out the vector's elements. So I'll give you a few minutes with a partner, go and fill in that code. It's in exercise 2.h. Compile it, run it. The run runs a couple tests, and you'll see if it works or not. Okay, so we'll resume in maybe 3 or 4 minutes. So your code probably looks something very much like this. And it's not very long. So I've got a for loop here. Vectors, just like arrays, start at index 0. They go up to their size, but don't include their size. So if you've got a 10-element array, they're numbered from 0 to 9. So I start at index 0. I go up to, but I don't include element size. And for each one of those elements, I can get at its contents, just like an array with the square bracket operator. So I get that integer and I print it out. Okay, so your code probably looked pretty similar to that. So very similar to arrays. Okay, so in order to use vector, you don't need to know this, but it's probably useful to understand, well, especially as computer engineers, it's useful to understand what's going on behind the scenes. So I'm going to show you what's happening as we actually run this code. Okay, so we're kind of looking inside vector. Okay, so here's the code we just wrote. And let's look at what happens. So person types 1. So we go through, well, let's just go step by step. Okay, so we hit this line. And that creates an object called integers. Its type is vector of integers. And it's created by the default constructor. The default constructor makes me an empty vector. Okay, so in memory, I've got this object called integers. And again, you don't need to know this to use vector, but if I now look inside of vector, what I would find is I've got, the reason it works so much like an array is it actually has a dynamically allocated array inside of it. Okay, so there's a pointer. Let's say it's called array, and that pointer points to some storage. This is up to the creator of the standard library, but a typical thing to do would be to say, okay, let's when you create that empty vector, let's give it room for 3 things. Okay, so this pointer inside of it, this dynamically allocated vector or dynamically allocated array, points at three elements, right? Enough storage for 3 integers. But we don't know what's in them. It also has a size variable, and that size is initialized to 0. So there's nothing in the vector. It actually has room to store stuff, but we have stored nothing. And it has another variable called capacity. And capacity is how much room it has. Not how many things are valid, but how much room it has. So this would be 3, because the default constructor in this standard library created out room for 3 things. Does that make sense? So now we go down to this line. We read one item in from our input, so we're going to get 1. That's what value will be. And we're going to call pushback to try to put it into integers. So pushback's a member function. You don't write any of this. This just all happens inside vector. Basically, it says, okay, size gets 1 bigger, so size becomes 1. And I'm going to store that 1 that you told me to store in the first entry of the vector. Okay, we go through the loop again. So we go back through this, and we're going to get number 3. And we call pushback, size becomes 2. We put the 3 in the next entry right there. Okay, so all looks pretty obvious. Go through the loop again. We get 8 from the person, size becomes 3. We put the 8 in the internal array. Now we go through and we get the number 7. And this one's more interesting because we're out of space. Okay, so we only had room to store 3 things, and we've stored 3 things. So inside the vector code, like the pushback member function, it checks, do I have room for this? It finds I don't have room for this extra number. It allocates a new array of integers, and it'll double the size. So it doesn't allocate 4, it allocates 6. And then it's going to copy over all the existing data. So it goes through all those 3 elements, copies them all over. It makes this internal pointer array point at the new storage, and it deletes the old storage to avoid a memory leak. And now it has room to store the entry, the 7. So it'll basically store the 7, increase size to 4, because you now have 4 elements. And it also knows that it has capacity for 6, because it doubled the storage. So that call to pushback, from your point of view, it was the same, but inside vector, a lot more happened. Okay, then we get the next number, it's a 2. That one's easy. Size becomes 5, and we store the 2. And now we're done. Okay, so notice when we're done, there's still a little bit of unused storage. right? Capacity is 6, but we should never try to access that last element. From the vector's point of view, its size is 5. It's got 5 valid elements. The fact that it has room for one more is an internal detail that you should not worry about. Okay. Does that make sense? Why do you think it grows by a factor of 2? So, I could have grown it by a factor of, just by 1. Okay, I had 3 elements, and I ran out of space, so I could have said, okay, allocate a new array with 4 elements. Could have done that. Doesn't do that. Doubles it. Any idea why? There's a very good reason for this. Maybe it's not obvious, though. Okay, so if you're not sure, I'll just show you it. Okay, so this is to make pushback efficient. Okay, C++ is a language designed for speed. It's designed for large programs and for fast programs. The standard library for C++ is also designed for speed. So we don't want a slow pushback. We want it to be fast. So the reason that we grow it by a factor of 2, or the standard library goes by a factor of 2, is what if I called pushback 1,000,000 times? It's perfectly reasonable. People do it all the time. Like I have a big loop, gradually sticking stuff in a vector, and it might be called 1,000,000 times. If I am doubling my storage every time, even if I put 1,000,000 things in my vector, the number of times I grow is logarithmic. I only need to basically grow it 20 times. And if it was 1,000,000,000, I would only need to grow it 30 times. So it's not very many calls to new, and it's not very many copies. Okay? What that means is that on average, pushback has order 1 complexity. Usually it just directly writes the element in and increments size. Once in a while, it has more work to do, has to call new, has to do a copy, but that's very rare because of the fact that it doubles every time. If you go through and do the complexity analysis, you'll find that the average or amortized complexity of pushback is order 1, which is very fast. Okay? If they actually had made it where it only added 1 element in each pushback, then the average complexity of pushback would have been order n, which would be bad, right? For 1,000,000 or 1,000,000,000, this would be wickedly slower. So, and that's throughout the STL. When you read the reference material in the STL, which you will in this course, you'll find that every function, they don't just describe what it does, they give its complexity. And the complexity in STL is basically the best you can do for that kind of data type. And the reason is they want the STL to be fast, so there is no reason to write your own. Okay? So pushback is fast. Yeah. So it's a good question. What about multiplying by 1,000? So there is a cost to doubling. Okay? The cost to doubling is this wasted space. Now, if I double, I can guarantee I never waste more than half my space, right? And I can also guarantee that I will never, if you actually go do the analysis, you'll find that even if you put 1,000,000 elements in this, the average element is only copied once. So that's a pretty good balance. Average element will be copied once, and the wasted space on average will be like 1/4 of the vector length, and never more than like 1/2, okay? If I did 1,000 times, okay, the average element is copied 0 times now, but my average wastage is like 500 times my storage, and my worst case is 1,000 times. So it's not a great space. They also have basically space bounds, right? And you want to keep your space bound also efficient so you don't run out of memory. So it's a balancing act. Does that make sense? Growing by 1 would be a really bad idea. Growing by 1,000 is a pretty bad idea. The standard library doesn't specify that it has to grow by 2, although that's common. If you grew by like 1.5, it would also still be amortized complexity of 1. It would be okay. In practice, they usually just do by 2 because it's easier to analyze and makes sense. Does that make sense? Okay, so, okay, any questions on that? So one thing I should say is don't get confused by this. The fact that I'm showing you this array inside and reallocation, you do not do any of that. That is all happening behind the scenes. If you now want to remove that from your memory and just remember that pushback is order 1, you can do that, okay? So, but it is, as computer engineers, it's really good to know, well, why is this fast? Okay, let's look at a few of the constructors that we have. One of the nice things about vectors, because it's a proper class, we have proper constructors. So the default constructor I already said. Here I'm going to make vec1. It's a vector of integers. Call the default constructor. I get size 0 vector. I can, if I give it 1 argument, so I say vec2 of 10, that will make my vector have 10 elements. They'll all basically be the default though, okay? The default of whatever that value is for that class. So for integers, the default is 0, so I believe these will all be default value of 0. And this one says, make my vector have 10 elements, set them all to -1. Okay, so you got a few useful constructor types. Okay, so I want to quickly go through a few of the. So vectors work a lot like what are called C-style arrays. What you used in 244 so far with new and delete are called C-style arrays. Vectors work a lot like that, but there are some differences. The differences are what make them vectors more powerful and more convenient. So let's look at those quickly. So here I'm making what's called a C-style array, dynamic array. So I take a pointer called A, and I make it point at an array of 10 integers that I just created with new. Here I make a pointer B, and I make it point at an array of 10 integers, different 10 integers that I just created. Or I could make vectors. So here I make vectors of integers, and I call them V1 and V2, and they both have 10 entries as well. Okay, so after these 3 lines of code, I've got 2 vectors that have 10 entries, and I got 2 C-style arrays that have 10 entries. You access elements the same way. Okay, so if I want to basically set the first value of my C-style array to 5, I would say A of 0 equals 5. Want to set the first entry of my vector to 5, I basically write the same code. V1 of 0 equals 5. Okay, if I write this code, let's see, for the C-style array, what happens? If I say A equals B, and A and B are both pointers to dynamically allocated memory, what happens? Is this good? Is this bad? Do you like it? What do you think? Yeah, so it's bad. It is bad. Why is that bad? Right, so that line basically just made this pointer A, which what used to point at this memory, it now points at B's memory. So now I should erase this. So basically both A and B point at the same memory now, and nobody points at the memory I allocated and had A pointing at. So I've leaked some memory. There's 10 integers that I no longer can get at, so they're a memory leak. And I now have 2 pointers pointing at the same 10 integers, which maybe I wanted, but probably I didn't. So usually you don't do that. Now you don't know how vector works that well yet, but basically the standard library is well designed. STL is a very clever, well done library. What do you hope that line V1 equals V2 would do? What do you think? You think? Delete, yeah. So what's the shorthand for what it should do? So yeah, it won't do a memory leak. That's true. It will get rid of any internal memory in V1. It basically does a proper deep copy, right? So it's going to make a completely separate copy of V2 and assign that to V1. And any memory, dynamically allocated memory inside V1 will get cleaned up. There'll be no memory leak, nothing. It all works perfectly. It's exactly what you would hope for. You wind up with still 2 completely independent vectors. They just both happen to have the same data. So vectors do deep copies, exactly what you would hope they would do. At the end of this routine, I should destroy A and B, right? I created A and B with new. If I don't create them when these pointers are about to go out of scope, I'm gonna lose them. So it's up to me to clean up after myself. I have to call delete. Now I already showed you that vectors actually have dynamically allocated memory inside them. Do I need to call delete on them? Do I need to do anything with these things if I'm about to leave this routine? What do you think? Do you want to call delete on them? Is it your desire to call delete? Would you like to write more code? So you don't have to call delete on them because you didn't call new to create them. So vectors do have memory inside them, but they're a proper class. They clean up after themselves. So if you didn't use new to create it, you never have to call delete on it. So the vectors don't have to be deleted. In fact, with the code I've shown you here, you cannot delete them, right? You didn't create them with new. You should not try to call delete on them. It'll be an error. So they're basically more convenient, right? They give me this random access just like an array, but I don't have to worry about calling delete at the end. I can grow them with pushback. I can do proper deep copies, etc. They're better. In this course, and frankly in the rest of your career, if you find that you're using a lot of arrays, you should stop and think, why am I writing this with arrays instead of vectors? Because once people learn vectors, they usually basically flip over to using them as their default data structure, not arrays. And that's what I recommend you do. Okay. Yeah, and if you find in your code, okay, 244, you probably wrote a lot of code with pointers. Is that correct? How many people love the pointers? Usually people don't love pointers. So pointers are important to understand computer hardware, and they're important to do certain tasks. But using things like std vector reduces the need for pointers a lot. So in this course, if you find you're writing a lot of code with pointers, you're probably doing it wrong, right? Like you do not generally need to be using pointers much, sometimes at all. And life is easier without pointers. So don't just start writing pointers all over the place because you just think, I probably should. You probably shouldn't be using pointers all over. Okay, bounds checking with vectors. So this is an important point. Operator square bracket does not create values. Okay, so in an array, you know that you can only access the elements that exist in the array. It's a really bad programming error to try to access something that's not in the array. With vector, it's the same. Operator square bracket lets you access entries that already exist. You can read them, you can change them, but you cannot create them. If you want to create them, you have to use other member functions like pushback. Now, C++ is designed for speed. That means the creators of C++ decided that operator square bracket would not check. Like on a vector, you could actually check whether or not you're in range, but by default, it doesn't. And because it's assuming the programmer knows what he or she is doing and that they're trying to get a fast program. That means that doing what's called an out-of-bounds read or write, or an illegal memory read or illegal memory write using this is a really bad programming error. It can make your program crash, but even worse, it can just make your program go crazy because you're just starting to write over other variables without realizing it. So it's really bad. So be really careful not to do that. You only use square bracket operator to access entries that you know exist inside the vector. So for example, here I've created a vector. It'll have size 0 because it's the default constructor. I call pushback. That's going to create one entry. It'll be entry, at subscript 0. I can do this. I can basically say, change the value at index 0 to -2. That's fine because index 0 exists. I cannot do this, right? If I type v1 of 1 equals 5, I am trying to access an entry that does not exist in the vector. Now, what happens? Something bad will happen, okay? This is called memory corruption. Valgrind would call it an illegal memory read, and so on. It's a really bad bug you want to get rid of right away. In Java, okay, how many people here know it's Java? Does anybody know Java? Another important programming language. It's very similar to C++. It was actually designed initially as a simplified version of C++. Its original name was C++... So I'm not kidding, right? Because C++ is a complicated language. So there was an argument of let's take C++ but make it simpler. So that was Java. And then they decided, let's make a different name. Let's call it Java. Java targets reasonably high performance, but not as fast as C++, so Java checks. So in Java, if you did this, you will actually get a runtime error. In C++, by default, you will not. Okay, but because this is such a nasty error, what we've done in this course, and it's something that would be done in essentially good software engineering companies, is we built another configuration. So you're going to notice in milestone 0 that you can build your project in several ways. One of the ways that you can build it in is called debug check. Debug check turns on extra error checking. One of the error checks it turns on is that this will now produce a runtime error. Basically, it tells the compiler, insert extra instructions, extra machine code, to check before you do something like accessing a vector element that it is actually inside the range. It slows your program down. Debug check actually slows your program down quite a bit, like about 7 times slower than the default one. But it will now check things like this. If your program's behaving strangely, you should, and actually just in general every once in a while, compile it in debug check mode and run it with all the extra checking to see if it finds anything. If it finds anything, you fix it right away. Because, well, what do you think will happen? If you have this in your program, well, basically, maybe this is too hard a question. You do not know what will happen, okay? Does anybody know what a seg fault is? You've seen a seg fault, probably, right? What causes a seg fault? Sorry? Yeah, so it is accessing illegal memory, so that line could cause a seg fault, but it doesn't have to, because a seg fault is when you access memory that does not belong to your program. The operating system now says you are a security threat, you're either incompetent or evil, but one way or the other, you're doing bad things to this computer, and I will not permit this, and it kills your program. That's actually the good outcome. It's a good outcome because it told you there's a bug. The bad outcome is, what if that, I'm accessing memory that's outside that vector, but maybe the memory outside that vector happens to be another one of my variables. Maybe it's a linked list right beside it. I just overwrote part of that linked list. What will that do? I have no idea, right? Like a line of code that has nothing to do with that linked list just changed it. No one knows how to debug that. So you run checkers like this. When they tell you that you're corrupting memory, you fix it right away, because the program is impossible to reason about a program that is corrupting memory, okay? So you think seg faults are bad, but that's the good outcome. The bad outcome is it just silently corrupts your data. Okay, so remember debug check. Okay, so vectors algorithmic complexity. So operator square bracket is just as fast as the square bracket operator for an array. It is order 1 complexity. Basically, an array, all the data is laid out in sequence. So if you want the millionth entry, the processor can just say, oh, it's a million integers. Each one is 4 bytes. I need to go to this pointer plus 4 million bytes. It can do that really fast. That's an addition and 1 memory access. Vector is just as fast because inside vector is an array. Okay, so vector's your friend. It's fast. I'm going to show you a small number of quick demos, and then you're done. Actually, before I show the demos, I'll mention this though too. You can't remember all of this, okay? Like what I've told you about the standard library, nobody memorizes all this. So in these slides that are posted on Quirkus, there are 2 of my favorite references for C++. They detail everything in the standard library. I have not memorized this. I go there all the time. You should too. Okay, so take a look at this short program. So I include vector, and I've got a little main program here that just calls this testVect function. All testVect does, it defines a number 100. So it's a constant. So n is equal to 100. It basically says, make me a vector of integers called v0. I'm calling the constructor with 2 numbers. This means I want 100 entries in my vector. I want them all initialized to 20. I want you to go from entry 0 to entry 105, and I want you to add the index to whatever's there. Okay, so after I run this for loop, the first entry in the vector, entry 0, should be 20. The second entry should be 21. The next entry should be 22, etc. And I print them all out. Okay, so first question is, do you have any concerns about this code? What do you think? Yeah, so it's bad code. I have indices from 0 to 99 exist, but I inexplicably go up to 105. So the last 6 indices I look at don't exist. So it's bad code. It's doing exactly what I said not to do. Okay, so I'm going to build that. Okay, so when I just type make, I get the default configuration, which is what we call the debug configuration. Okay, and you can see the options passed to the compiler here if you want. I'm now going to run this. Let's see what happens. Okay, so it prints out all the entries in the vector. And the first one should be 20, and it is, and then 21. So that all looks good. It gets up to entry 99. It should be 119, and it is. But then entry 100 is 100. Entry 101 is 101. 102 is 1143. 104 is 8 billion. It gets increasingly bizarre. And it's because I've gone beyond the end of my array, my vector. These things weren't initialized to 20. I have no idea what I'm looking at here, right? Like this is some random bit of data. I have no idea what I've done, right, with the last 2 lines of this. I didn't get a seg fault, which is actually unfortunate because I've corrupted some of my other variables. So this is actually going to be really hard to debug. It would have been better if I got a seg fault. Okay, so what I'm going to do now is I go make clean. That gets rid of the old program. I'm going to say make conf equals debug check. So this is one of the other configurations. It has more options. You see that there's these funny options turning on what are called sanitizers, turning on standard library debugging, and so on. You don't have to worry about the details of this. This is relatively advanced. But basically, we're telling the compiler, put all sorts of extra error checking code in. The program's going to run slower, but it's going to check everything we can think of, including that you don't go outside of a vector and a bunch of other stuff. Okay, so now if I run this, I get an error. Okay, so what happens is I see all the output up to vector element 99. That's all legal. And then it tells me I'm in the standard library in the vector file. I'm in a certain vector function. And the most important information is this. It says you attempted to subscript or access a container. I know it's a vector from all of this output with an out-of-bound index 100, but the container only has 100 elements. So I used index 100, but this vector only has 100 things in it, which means index 99 is the last thing I should have used. It killed my program. It told me the address of the vector that was the problem. This will help me a lot, right? To track down if my program is behaving bizarrely, well, I should go look at the vectors. And in fact, I can even bring it up in the debugger and look at that memory address if I want. So it's a big clue. So debug check does some of the same things as valgrind. They overlap some, but it does some additional things that valgrind can't do. They use different, their goal is similar, but their technologies are slightly different. Okay, so my last set of demos, I think I'm going to keep you guys a few minutes over if that's okay. If you've got to really go, then I understand. Okay, so I'm going to show you, okay, this is a program that is doing sort of a pointless computation 50 times on every element of a 10 million element array. Okay, so we build a big array. It's got 10 million elements in it. And then 50 times we go through the whole array doing a computation on every single element in it. Doesn't matter what the computation is. It's just to basically see how long this takes. How long does it take to do 50 computations on every element with 10 million element? Right now, C-style array. Okay? So, because you can see I'm allocating with new a C-style array. So I'm going to compile this. All right, and I use the default build, so it's what's called the debug build. Linux has a handy command called time. Tells you how long a program takes. You just type your command after it. Okay, so this prints a bit of output. And this is how long it took. It took 0.99 seconds. So 0 minutes, 0 seconds, and 99 100ths. Okay? So remember that number, 0.99 seconds. That was with the arrays that you've been using in 244. Now, before I change this to vector, does anybody know what compiler optimizations are? You heard of this? Okay, so there's no reason you would, but basically, what I'm going to do now is I'm going to rebuild the program in what's called release configuration. Okay, so the default configuration debug compiles your program in the most basic way possible. Every line of C++ is basically translated directly into machine code without any reordering, any attempt to make it faster. The reason that's done is the compiler runs fast, and more importantly, when you go into debugger, the code executes in the exact order that it's written, and every variable you wrote you can look at, okay? So that's called debug configuration. Now I'm running a release configuration. The key difference is this 03. Okay, that says optimization level 3. Now what the compiler does is it's told, don't just translate this in the simplest way, make the program fast. It will reorder operations. If it finds that 2 variables are a copy of each other, it gets rid of one of them. If it decides that this function's really short and I'm wasting time calling it, it can paste all the code from that function into another function, and a whole bunch of other stuff, okay? So it'll try to change divides into multiplies when it can, all sorts of things. Now, the reason we don't do this all the time is if you run that in the debugger, you'll actually find like this variable doesn't exist because the compiler managed to get rid of it. So you can't see it. You'll see sometimes that you're single stepping and you go to this line, then back to that line because the compiler changed the order. And it did it in a way where no one can tell. Final answer is guaranteed to be the same, but the steps may be reordered. That makes it harder to debug, but it makes it faster. So I'm using the up arrows to go back to my old command. Okay, it took, instead of 0.99 seconds, it took 0.46. So it's more than twice as fast, and I didn't do anything except build it with optimizations on. And for more complicated programs, instead of 2x, it's often 3 or 4x. Okay, we have speed tests in this course. Okay, so you're going to use all of these configurations. When you're trying to pass speed tests, you want to use release. Otherwise, you are just beating yourself up for no good reason. But when you're debugging, you want to use the debug release in the debugger. And if you're just worried about memory corruption, you want to try debug check. Okay, so you're going to try all of these things. Now that's all with an array, like a C-style array. So remember that number. I'm going to change just one line of code. Instead of creating a C-style array, I just created a vector. But vector is so similar in its usage that I don't have to change any of the rest of the code. So it's going to do the same thing, but it's just going to use a vector. We're going to see if it's any slower. Okay, so the time was 0.46 seconds. I want to check with release. You always do speed testing with release because you want to see the impact of optimizations. Okay, use the up arrows. I can go back to my old commands. All right, 0.47. Okay, so 0.46, 0.47, basically a tie. So there's no real downside to using a vector. Okay, and then my absolute last demo, I'm going to show you one last thing that's short. Okay, so this is not C++. This is the same, this does the same thing I showed you, but what language is this? This is Python, right? I don't have to give anything a type. That's kind of convenient. Code's a bit shorter. That's kind of convenient. But this does the same thing. It makes a list of 10,000 things, and in Python, a list is really an array. So it's kind of a naming thing, but this is their equivalent of an array. I do the same computation. So let's run it. Oh, actually, I need to go time. Okay, so it's running, and we have a little bit of time to chat. So remember, the C++ version took less than half a second. This one's still going. So Python is a good language. You should learn it. How many people know Python? Okay, so if you don't know it yet, you'll learn it in 3rd or 4th year. Because it's highly productive, right? You don't have to declare types. You don't have to compile it. You notice I never compiled it. I just ran it because it's actually an interpreted language. But it took 23.5 seconds, okay? So I did the calculation at home. It's 55 times slower. So C++ is built for speed and for big programs. Python is built for I want to make it work quickly and tie things together. They both have a role, but this is why you don't use Python for everything, right? 50 times slower, is expensive. Now you may have heard that there are important machine learning frameworks like PyTorch that are in Python. So machine learning is very compute intensive. So how do you think those things fit together? Why do they do it in Python? And maybe you can't answer that. That seems contradictory, except PyTorch, which does machine learning in Python, the control code is in Python. All the heavy lifting is calling functions which are written in C++. Okay, so Python can call C++. And if you're going to do something that is compute heavy, yeah, the way it's done is the control code's in Python, but all of the heavy lifting is Python libraries that are actually calling C++. So that's why you get kind of these mixed things. In the end, it's good to know more than one language, but this kind of shows you there is a performance cost for not having to declare your types and not having to compile. Okay, thanks everybody. Have a good weekend.